For the next several videos, we're going to be concentrating on three different tests: the ratio test, the root test, and comparison test. So let's first take a look at the ratio test. We have three different situations we need to look at. So this is what the test says. If the limit as n goes to infinity of absolute value of a to n plus 1 over an, this is r, and if we're going to call it r, and if r is less than 1, then the infinite series n equals 1 to infinity of an is absolutely convergent. The other scenario is the limit as n goes to infinity, same thing, absolute value of an plus 1 over an. This again is equal to r. And if r is greater than 1, then the infinite series is divergent. And the last scenario is if the limit as n goes to infinity, absolute value of an plus 1 over an equals r. If this is actually equal to 1, then the test is inconclusive. Now, why do we need or want this thing called the ratio test? Well, we know about the integral test, and the integral test really works quite well, but it is also limited. What if I had a factorial in my sequence, which means it's in the infinite series? How do you integrate that factorial? That can be a little bit difficult to do. So there's different techniques that we want to take a look at and be able to apply them in different situations. Now, just to make sure we're on the same page here, we have this infinite series of an's. And what I'm going to do is I take the next term. This is an plus 1, the next term divided by the previous term. So it's the ratio of consecutive terms is what this actually is. So since in the limit this ratio is less than 1, what this is really getting at is the idea that not only does the sequence go to 0, but it must go to 0 fast enough in order to converge. So that's the basic idea behind this ratio test. Let's go ahead and take a look at a quick example here. I want to figure out if this series is convergent or not, and I'm going to use the ratio test. So I'm going to take the ratio of consecutive terms. So I will take a look at the limit as n goes to infinity, the absolute value of 1 over 7 to the n plus 1, remember this is an plus 1 in the numerator, divided by an, which is 1 over 7 to the n. Now, these are all positive terms, so this absolute value thing won't have any meaning here. I can actually drop the absolute value at any point now. So this is actually going to be equal to the limit as n goes to infinity of 7 to the n over 7 to the n plus 1, which is equal to 1/7. So this is what I'm thinking of as being r. And you notice that this is less than 1. Therefore, this infinite series, oops, that should be a 7, is absolutely convergent. Now, I'll talk a little bit later about the idea of absolute convergence versus conditional convergence. So let's take a look at another quick example here. I want this infinite series, n equals 1 to infinity of 1.3 to the n, and I'm trying to figure out whether or not this thing will converge or not. So if I use a ratio test, I could integrate this, but if I use the ratio test, I'll take a look at the limit as n goes to infinity, absolute value of 1.3 to the n plus 1. This is the a n plus 1th term, divided by 1.3 to the n. That's going to be equal to simply 1.3, which is greater than 1. Therefore, this infinite series is divergent. Now, we may have also realized that this is a geometric series, where in this case r is greater than 1, therefore we would have known that it's divergent. If you look back at that previous example, this is actually the same as the sum n equals 1 to infinity of 1/7 to the n, because 1 to the n is just 1. Well, this is also a geometric series with the absolute value of r less than 1, therefore convergent. So this technique actually agrees with stuff that we've already done.